Hello, my name is Myungeun Lee. I am very pleased to share our Radiomic study with you. The title is Quality of Radiomic Features in Glioblastoma Multiforme, Impact of Semi-Automated Tumor Segmentation Software. Radiomics or radiogenomics has been a popular subject of study topics in recent years in many cancer imaging researches. Radiomics, the high throughput extraction of a large amount of image features from radiographic images, is really an attractive study subject in this era of big data sciences. In particular, several interesting studies have shown a good potential of applying radiogenomics on GBM in discriminating molecular subtypes of the tumor, as well as predicting patient survival. Although issues remain regarding the reliability and variability of radiomic features arising inherently from the tumor segmentation procedure. In spite of the popularity of radiomics research applications, studies on the quality of the radiomic features are surprisingly rare, especially in applications to the GBM. This motivated us to embark this study. We attempt to strictly assess the feature quality of radiomics for GBM. Reliable tumor segmentation is one of the main challenges of radiomics analysis. This is the first step in radiomic feature analysis procedure, and thus can be considered as a major source of variability in radiomics. Use of semi-automated software for tumor segmentation is a preferred option in radiomics studies since it offers markedly improved efficiency and may allow the avoiding inter-observer variability in tumor delineation. In order to assess the quality of radiomic features, we employed two different semi-automatic methods with two different raters. Data population. MR images of 45 GBM patients were downloaded from the National Cancer Institute, the Cancer Imaging Archive. Study patients consisted of 29 males and 16 females. The average age of male patient was 56 years and 57.5 years for the female patient. We used two MRI sequences for segmenting different tumor tissue components. In Figure 1 shows an example TCGA GBM case. You can see segmented ROIs for contrast-enhanced, necrosis, and non-insensitive to high signal intensity area indicated by a red, a green, and a blue color respectively. This slide shows an overall procedure of our study. The post-contrast and flare images were first registered, followed by tumor segmentation using two different semi-automatic methods by two different raters. Subsequently, image features were extracted from segmented tumor ROIs using the computer algorithm. Finally, we evaluated the quality of the features in terms of robustness, NDR, and redundancy. Tumor segmentation was carried out by two experienced rasters for each tumor tissue components using semi-automated segmentation software tools. We used two different software tools, Tumor Prism3D, which is an in-house software tool developed in our laboratory, and 3D Slicer, which is a free software. Tumor segmentation procedures for the two software tools are illustrated in Figure 3. With the Tumor Prism3D, the user drew an initial ROI within the tumor, followed by automated tumor segmentation using the deformable-based algorithm. With the 3D Slicer, the user defined the background and foreground objects by drawing sketches on them, followed by automated separation of tumor from background tissue using the grow-cut algorithm. Thus, 4 computer-assisted tumor segmentation datasets were produced for 3 different tumor tissue components in each patient. In addition, for evaluation of the accuracy of the computer-assisted semi-automated tumor segmentation, we created a reference tumor segmentation dataset for the same cases using an in-house software by two radiologists in consensus. The accuracy of computer-assisted tumor segmentation was evaluated by calculating the similarity between the reference and the computer-assisted tumor segmentation. We used the dissimilarity coefficient measure for calculating the similarity between two segmented tumor volumes. The similarity measures were obtained from the binary tumor masks generated from the segmented tumor volumes. The dissimilarity coefficient measure represents the relative overlap between two binary volumes data and is expressed in equation 1. We considered the three groups of radiomic features such as the first-order statistic, texture, and morphometric features. First-order statistic describe the pattern of pixel intensity distribution within the segmented tumor RY. Certain first-order statistic features were extracted from the three tumor components RYs, thus generating a total of 42 first-order statistic features. Texture features represented the changing patterns of pixel intensity among neighboring pixels. We extracted 22 grade-level co-occurrence matrix-based and 11 grade-level luminance matrix-based texture features from the three tumor component RYs, thus generating a total of 99 texture features. Morphometric features were descriptors of the size and shape of the tumor. We extracted 11 morphometric features from the three tumor component RYs, thus generating a total of 33 morphometric features. All feature extraction was performed with a software program written in MATLAB. The three groups of extracted features are illustrated in Table 1. We evaluated the quality of features in terms of stability, normalized dynamic range, and redundancy. The first evaluation index is the stability of imaging features. Stability has been often used for quality assurance and selection of robust features at the first step in radiomic feature analysis. Stability represented the arrangement of features derived by two raters using the computer-assisted tumor segmentation procedure and was tested with the intra-class correlation coefficient. We classified the range of ICC into three groups: good, moderate, and poor stability, as follows. The second evaluation index is feature dynamic range. Dynamic range has often been used as a measure of informativeness of radiomic features, as a certain degree of perturbation is unavoidable in extracted radiomic features due to inherent variability from different sources. Features with higher dynamic range are regarded as more robust to feature perturbation and thus regarded to possess relatively good information compared to those with narrow dynamic range. Normalized dynamic range describes the relative range of feature values as compared to the average value was expressed in equation 2, and they are calculates the difference between feature values of top 10% and bottom 10% samples from the study population, which was then normalized by the absolute mean feature value. Average feature values from two raters were used in NDR calculation. Redundancy denotes the similarity shared among different features. Different features reflect unique aspects of tumor phenotype and are expected not to resemble each other. However, in practice, computer-extracted tumor features often exhibit similarity among one another, resulting in redundancy in the Radiomic feature pool. Therefore, we examine the redundancy of Radiomic features in GBM by assessing their cluster properties. Features belonging to the same cluster were regarded as redundant. We applied the consensus clustering technique using an R package consensus cluster plus. With this package, we obtained the cluster consensus for its feature cluster, which was defined as the average consensus between all pairs of features belonging to the same cluster. The CC indicates the robustness of the cluster over multiple runs of experiment with the reasonable parameters during cluster generation procedure. We chose 5 clusters that gave the most robust CC. We regarded those clusters with good, moderate, and poor robustness, like this. In addition, we assessed the cluster agreement for each feature cluster, which was defined as the average agreement of feature pairs belonging to the same cluster derived from 2 different raters. The Rand Statistic was used to measure the cluster agreement as shown in equation 3. We regarded those clusters with good, moderate, and poor agreement. Result. Table 2 shows an accuracy of the segmented tumors obtained with the 2 semi-automated tumor segmentation tools as assessed with dice similarity coefficient. Tumor segmentation accuracy in our study turned out to range from 0.71 to 0.84 depending on differing raters and software tools. It also turned out that 2 types of semi-automated tumor segmentation software tools by different tool raters produced 2 masks with a similar accuracy. Figure 4 shows the example segmentation results of the 3 tumor tissue components with the 2 semi-automated segmentation tools. Contrast enhanced, necrosis, and non-enhancing to high signal intensity area were indicated via red, a green, and a blue color respectively. Case A represents a case with a similar result, while case B represents a case with a slightly different result. Shown here in Table 3 are stabilities of the 180 radiomic features as assessed with ICC. Overall, the 2 semi-automated software tools produced similarly stable features. With Tumor Prism3D, 40 of 42 first-order statistic features, 88 of 99 texture features, and 36 of 39 morphometric features showed high stability. With 3D slicer, 41 of 42 first-order statistic features, 86 of 99 texture features, and 35 of 39 morphometric features showed excellent stability. However, a few of the texture and the morphometric features showed poor ICC, which suggested that those features might be more susceptible to rater-dependent differences in tumor segmentation. Of the total 180 features, only 37 and 40 features showed good NDR, while 44 and 40 features showed full NDR with Tumor Prism3D and 3D slicer respectively. Among the 3 feature groups, first-order statistic group showed relatively higher NDR. 39 out of 42 features showed good or moderate NDR with both software tools. In contrast, a majority of features that showed full NDR were in the texture feature group, In morphometric feature group, a majority of features showed moderate NDR. Summarize of NDRs for the GBM Radiomic features is shown in Table 4. This slide compares the feature redundancy maps of two segmentation tools. As you can see, 5 distance clusters appeared similarly with two software tools. In both consensus maps, the size of cluster 1 was considerably small with moderate robustness and agreement, and the other 4 clusters were of similar size with good robustness and agreement. This result again appeared to show that both software tools in this study produced sufficiently reliable segmentation results. We also looked into each cluster to see if clusters have different feature characteristics. Figure 7 illustrates the decomposition of each feature cluster into 3 feature groups: first order, texture, and morphometric. Overall, cluster 1 was composed solely of morphometric features. Clusters 2 and 5 were composed mostly of first order statistic and texture features, and clusters 3 and 4 of all 3 feature groups. Figure 8 illustrates the decomposition of each feature cluster into 3 tumor tissue components. Clusters 1 and 4 were composed mostly of contrast-enhanced and non-enhanced to high signal intensity tissues. Clusters 2 and 3 were of contrast-enhanced and necrosis, and cluster 5 mostly of non-enhancing to high signal intensity. Notably, the same tendency was observed in both clusters maps derived with Tumor Prism3D and 3D slicer. This slide shows the robustness of the 5 clusters. The CC values representing the robustness range from 0.73 to 0.98, and their agreements as assessed with RS ranged from 0.62 to 0.97. Notably, the CC and RS expect the smallest cluster were all higher than 0.8. The size of cluster 1 was considerably small with moderate robustness and agreement, and the other 4 clusters were of similar size with good robustness and agreement. Our findings indicate that the 5 feature clusters found in this study are inherent to the radiomic features in GBM and not dependent on segmentation software. In this study, we investigated the quality of radiomic features in GBM. We categorized the radiomic features into first-order statistic, texture, and morphometric feature groups and assessed their quality in terms of stability, normalized dynamic range, and redundancy. The segmentation results are in substantial agreement with 2 semi-automated segmentation tools and between raters, and the quality of a feature was overall consistent. Our study has several limitations. First, only 2 types of software tools were used for evaluation. Semi-automated segmentation tools employ sophisticated algorithms to reduce users' manual intervention as much as possible, and provide reliable segmentation results at the same time. 2 our best knowledge crow-code algorithm and deformable model-based algorithm were 2 representative semi-automated algorithms for segmenting tumors on medical images, and were implemented in the 3D slicer and the Tumor Prism3D respectively. Second, stability of radiomic features was evaluated with a single-scan dataset. Thus, variation of segmented tumor volumes due to inconsistent user intervention is regarded a major source of instability of radiomic features. Varying physical state of patient and scanner might cause additional perturbations to radiomic features. However, such a dataset was not available to our study. Therefore, our stability data should be interpreted with caution in that they are applicable only to limited sources of variability. In addition, our study used an MRI dataset acquired with a relatively simple protocol. As a variety of first sequences are used in MR imaging, it is obvious that images acquired with different first sequence would bring about different feature quality in GBM study. For example, diffusion imaging. Thus, our study result cannot be generalized to all MR GBM studies. In conclusion, the use of two different semi-automated software tools by different raters showed similar high stability in radiomic features in GBM, regardless of the difference in raters' experience. This indicates that semi-automated software tools provide sufficiently reliable segmentation output and help overcome the inherent inter- and intra-rater variability from user intervention. However, significant differences existed in normalized dynamic range among features, which suggested that features convey information with differing strengths. Among the feature groups, texture features show the weakest normalized dynamic range. A total of 180 radiomic features in our study was highly redundant and compressible to 5 distinct clusters. However, significant differences existed in the proportion of features according to the tumor tissue components appearing together. A well-established quality assurance procedure has an important role in the future advancement of radiomics and translation into patient care. The findings in our study may be useful in guiding the development of quality assurance procedure of the radiomics pipeline, particularly for GBM. Thank you for your listening.